So in this last video about optics, we're going to look at light a little bit differently than we have before. Um, Good thing is, in this section of the notes, I don't think I left any blanks, so there won't be any writing to do unless you want to copy down a few little notes in the margins or on the diagrams. So what we're getting into is wave optics. So a lot of you probably already know that one of the weird things about light is that not only can it be treated like a particle, it can also be treated like a wave. So, where is that? Not, nope. Here it is. Alright. So, neat little picture that I've had on my phone for I don't even know how long, and I finally get a chance to use it. So, light is simultaneously a particle and a wave. So, we're going to be looking at its wave behavior today. So classical physics that we've been doing so far only deals with particle properties. So now let's get into some of the wave model stuff. So first one that you have a little bit of experience with from doing that simulation is the double slit experiment. So wave theory of light came about from this guy Thomas Young when he did his double slit experiment in 1801. So we mention his name just because you'll so often hear Young's double slit experiment. So you better know what someone is talking about if they mention Young's double slit experiment. So it proves that light has wave properties because um, if you remember on the screen over here, the dark spots and light spots happen because of constructive interference and destructive interference. So when multiple waves build each other up, they coincide in the same spot, so you get a little bit extra, or they kind of happen in opposite directions in one spot and cancel each other out, so they kind of destroy each other. So that behavior is unique to waves because only waves can occupy the same space at the same time. Particles can't do that. So like you have seen in the simulation, we have a setup like this in which we have some kind of barrier blocking a light source from some kind of screen, and only two small slits allow the light to get through. So you're shining on a screen, you guessed it, two very narrow slits that are separated by a distance d. So this slit is d away from this slit. A second screen is set up a distance L away. So first screen L, second screen. So the light passing through the two slits is able to shine onto that spot. So let's say that we have some coherent light. Coherent just means that you only have one wavelength, only one color of light. That's why when you were doing the simulation, you had to kind of pick one color and then you could change the color around, but it was always all one color. So you have that light of a single wavelength, the coherent light traveling in phase, and the light hits the first screen with the two slits. So both of those slits are smaller than the wavelength of the light. So since they're smaller than the wavelength, the light is able to spread out and distribute itself across the screen, kind of what you saw in the picture here. Um, so light, it's coming in perpendicular to the screen, but then once it passes through the slits, it kind of forms that circular pattern that you see there as it spreads out. Alright, so at any point that you look at on the back screen, we'll call it point P. There's light from two different sources, one from each of the slits. So you'll have some from the top slit, some from the bottom slit, both going to point P. So the line that joins point P to a point exactly between the two slits, so right here in the middle of D, will intersect. Alright, threw myself off there a little bit. I had to pause and reread this sentence. So the line that joins point P to the point halfway across D there forms this angle theta to this perpendicular line. So if you could cut D right in half, the line that would connect that point to P forms angle theta here. So we're going to assume that the two screens are very, very far apart. So this distance L is a lot bigger than the distance D is. So you might want to call that a far field approximation. The site that you're viewing is far away from the source. So that's going to allow us to assume two other angles, angle A, or alpha, and angle beta, that are formed by almost similar lines, the lines that connect the center of the slit up to point P. So center of the slit to P, center of the slit to P. So that'll form angle alpha, angle beta. If we use the far field approximation, then those are both about the same as theta is. The farther away, the closer they are to all being the same. So if we're looking at light from the bottom slit that we have drawn here, it's traveling a distance of, so this distance here is d sine theta more than light from the other slit. It has a little bit extra to go. So this segment and this segment would be equal. So as a result of that extra little bit of distance that light from the bottom slit has to travel, they will arrive at point P out of phase by this much, because we said before they all have the same wavelength. So they start out all together. If one has to travel a little bit farther, it'll get a little bit out of sync with the rest. So that's what it means by out of phase. So if this d sine theta, the extra little bit that it has to travel, is equal to some number plus 1/2 times the wavelength, where n is just some integer, then the two waves are half a wavelength out of phase, which means they destructively interfere. So if the two waves are canceling each other out, there's not going to be any light left to hit the screen there. So those points are called minima, where the intensity of the light, the brightness, is the lowest. You have the minimum amount of light available. But if we have d sine theta equal to some integer multiple of the wavelength, then the two waves are still in phase, and they'll be able to constructively interfere. So you get the most light you could possibly have hitting the screen at that point. It would look the brightest, and since we have the maximum amount of light available, those points where d sine theta is an integer multiple of lambda, the wavelength would be called maxima. So just quick refresher on destructive and constructive interference. If your waves are out of phase by half a wavelength, then when one wave is up at the top, the other wave is down at the bottom. They would completely cancel each other out here. And then they switch back and forth, back and forth. So if you're off by half, you'll get a dark spot. But if we have them back in phase, you can kind of see how the high spots, like one of the lines is solid here, one is dotted. When the high spots meet together, they get extra high. Here when they're high, they get extra high. So constructive interference at the bright spots. So the far screen is going to alternate between patches of constructive and destructive, because that d sine theta will change depending on where you put the point P. So the light shining through the two slits, which you've seen on the screen, would follow this sort of pattern. We have dark bands and bright bands all up and down the screen. So the bright, um, the pattern is brightest right in the middle where theta is 0, so the point P straight across from the center of D. That's called the central maximum. So if you ever run into a question about double slit, um, the double slit setup on the test, then you'll likely be asked to calculate how far away the central maximum is from the next bright spot. And there is an equation for that we're going to get to in a second. So that distance, for apparently reasons that are too involved to address here, is a function of the wavelength, the distance between the slits, and the distance between the two screens, which all of those things you should have tested in the simulation. So wavelength over slit separation is equal to, what do we call x? Oh, the x, that's what we want to find, the distance between the central maximum and the next bright spot. And L would be the distance that separates the screens. So you could have an equal chance of running into a problem that involves a single slit rather than double slits, and that's what we'll get into next. So diffraction in general is the way that light or any kind of wave bends around some kind of obstacle. So it causes interference patterns like the one we saw up above. So a diffraction grating is a screen with a bunch of these slits. Each one is spaced the same amount of distance apart, so some distance d. So the analysis you would have there is just the same as in the double slit case. You'll still have a maxima where that extra bit of distance still keeps both of the waves in phase, and minima where they get knocked out of phase by half a wavelength. So the only difference here is that the pattern doesn't really fade out as quickly on the ends. So single slit diffraction here. We could bump into that on the AP test. The setup, like I said, just the same as the double slit, except just with one slit. Oh, an arrow, I thought that was a line. Alright, so this time instead of D being the separation between the two slits, D is going to be the width of the slit itself, and theta will be the angle between the middle of the slit and some point P. So the overall setup still looks the same. So now that we have this much bigger open spot, there are a lot of different paths that light is able to take to point P. If you look at any point in that slit, it could travel from there up to point P. So really, the diffraction pattern that you see is caused by the superposition of an infinite number of waves rather than just looking at two. So the paths that we have coming from the two edges of the slit. So here it would be the one from the bottom, here's the one from the top. Since they're the farthest apart, they're the ones that are going to have the biggest difference in phase. So we really only need to consider those ones to find out where the maxima and the minima would occur. Everything in between those would kind of follow suit. So single slit diffraction, nowhere near as noticeable as the double slit stuff. So we'll have a maximum when n is 0, and it's really, really bright. But all the other ones, you barely be able to tell that they're there. So you don't really have to worry about the diffraction caused by both of them individually, because, well, what that's saying is a double slit is just two single slits put together, and we're saying here that you can't really tell, but then um, when you put two of the slits together, then apparently it makes a big deal. So what we're just saying here, um, we don't have to worry about treating the two slits as two individual slits. We can look at them together. On In the WebAssign, there's a good chunk of questions dedicated to this slit interference stuff and diffraction grading, so you'll get a little bit of practice using that equation. Alright, I think last topic is polarization. So light, we said before, is a transverse wave, so it oscillates perpendicularly to the direction that it's traveling. So it'll move up and down, or it'll oscillate up and down as it moves off to the left, right, what have you. So a wave is actually free to oscillate right and left or up and down any angle between vertical and horizontal. So, I mean, it could happen in any direction, not necessarily always just one. So there are some kinds of crystals that have a special property of polarizing light. So they force the light to oscillate only in one certain direction depending on how the crystals are aligned. So um, apparently it's common in Polaroid discs. I think we have some in the prep room. I'm going to have to dig those out tomorrow so we can take a look at those. So human eye actually can't tell the difference between a polarized beam of light and one that's not polarized. So here is a bunch of light coming in, oscillating in all different directions, passes through a Polaroid disc, and only one certain wavelength is able to, or one certain direction of oscillation is able to pass through. But if you have polarized light passing through a second Polaroid disc, then the light gets dimmed more and more as the second one is out of alignment with the first. So with the first disc, you can see here, only wants to let the up and down light through. Then we go from all the crazy directions to up and down. The second Polaroid disc only wants to let horizontal light through, but the first one only let vertical stuff through, so nothing is going to come out ultimately. If we look down a little bit at the next example, same initial setup. So we have crazy every direction, gets filtered out to only vertical. This one isn't turned quite so much, so a little bit is able to get through in that direction. And then in the last one, if we have them aligned together, then all the light is able to pass through. So polarization, pretty simple. We don't have to worry about any kind of equations for that. In general, anything that you encounter about wave optics, if it won't mostly, for the most part, be quantitative. It could be. There are a couple equations left on the equation sheet that we haven't talked about in previous videos and we talked about here, and you'll work with them in WebAssign. But for the most part, it's going to be all qualitative. So doubly important that you understand more so the big picture, what's going on. It's not going to do you a lot of good to just memorize how to use the equations, the d sine theta and n lambda and n plus 1/2 lambda. So if you don't understand why it's happening, you will likely not be able to perform very well on the wave optics sections of the test. So another common type of way that you'll be tested for wave optics will be, do you understand these certain terms? So we've got a lot of them in this unit: diffraction, the way light spreads out around a barrier; polarization, how we limit the type or direction that light is oscillating; reflection, the bouncing, refraction, the bending, interference, do they add up or take away, and dispersion, how it kind of spreads out based on wavelength. So they're all different types of manipulations, and you may find a question or two that describe a situation that's going on, and they may ask you to explain what's the word for that. So, quick example, which of the which of the following phenomena does not affect the direction of a wave of light? So, dispersion, yes. Um, Polarization does not. It affects the oscillation, but not necessarily which direction the wave is traveling. Diffraction definitely does. Reflection for sure does, as does refraction. So answer here would be B. Polarization affects how light is polarized, so how it oscillates, but doesn't change its overall direction. So that is it. We have a little table of all our formulas, and then into the practice questions.